Chef. Right. Right. Now we'll start. Give me a few more minutes. We'll start. Give me a few more minutes. Yes, good evening. Mm, okay. I think we started normal reaction forces and we were discussing two cases. Now we'll continue from that. Mm, okay. Can someone reply what was the last case that we discussed under normal reaction forces? Can someone reply what was the last case that we discussed under normal reaction forces? Last case? The last case. Can someone reply the last case that we discussed? Is it case 4 or case 3? I think we discussed case 4, right? Okay. Now put a case number 5. Case 5. Case 5. Write down. Case 5. Okay. Now, in case number 3 and case number 4, a vertical force is acting on the object downwards or upward direction. In that case, what would be the normal reaction force? Am I correct? In case number 3, normal reaction force acting on the object is vertically downwards. In case number 4, in case number 3, the external force acting on the object vertically downwards. In case number 4, external force acting on the object vertically upwards. Now, case number 5, if there is an external force acting on the object inclined direction, in that case, how to find the normal reaction force? Okay, case number 5. Case number 5, if there is an external force acting on the object inclined direction, inclined. Okay. Now draw this diagram with me. Draw the diagram with me. Draw the diagram with me. Okay. Now that's an object. That object is on the ground. That object is on the ground. Case 5. Object is on the ground. Case number 3 and case number 4, external force acting on the object is vertically downwards, different vertically upwards. In that case, I taught you how to find the normal reaction force on the object. Now, suppose if there is an external force, acting on the object in this direction, capital F external force, I say inclination to the horizontal is theta. Inclination to the horizontal, let's say theta. This inclination theta. Then shall we mark the forces? Now we learned only weight, gravitational force and normal reaction forces. Any object that has a weight. So weight force of this object, mg. Mass of the object, I say simple m. Mass, simple m. Weight, mg downwards. In addition to weight, we know there is normal reaction force because there's a contact between the ground and the bottom surface of the object. So whenever there is a contact between two surfaces, there will be perpendicular forces acting on the objects. Now here there's a contact between the ground and the bottom surface of the object. Then normal reaction force on the object upwards. Normal reaction force on the object upward direction R. Now what's my target? My target is to find capital R. My target is to find capital R. How do we find capital R? How can we find capital R? Now, when you want to find capital R, simple mg, they are vertical forces. Capital F, external force, is inclined. So therefore, I advise you to resolve capital F force into two perpendicular components, horizontal and vertical. Your first step is resolve capital F into two perpendicular components, horizontal and vertical. If you resolve it, what is your horizontal force component? F cos theta. F cos theta. Resolve it. Horizontal component will be, now I taught you how to resolve a vector in vector section, and when I was explaining projectile motion also, I explained how to resolve a vector. I think you can remember. Then this component will be F cos theta. F cos theta. What is the vertical component of capital F? F sin theta downwards. F sin theta downwards. F sin theta. F sin theta. Mass simply. Now it's very clear that this object moves to the right side direction. If this object is moving, this object should move to the right side direction. Why this object should move to the right side direction? Because there's an external force acting in the horizontal direction, F cos theta. Because of F cos theta force component, this object moves to the right side direction. But this object does not move vertically upwards. Am I correct? This object does not move vertically upwards. That means we can say this object is at the vertical equilibrium. Okay. Now I resolve capital F into two perpendicular components, F cos theta, F sin theta. Because of F cos theta component, object moves horizontally, but this object does not move vertically. Then we can say this object is under vertical equilibrium. So therefore, I can write down, considering vertical equilibrium, considering vertical equilibrium, I can say that. Then, if this object is under vertical equilibrium, we know that upward addition of all the upward forces must be equal to addition of all the downward forces. Addition of all the upward forces must be equal to addition of all the downward forces. Upward force capital R is upwards, a simple mg downwards, F sin downwards. Then R must be equal to upward forces R must be equal to downward forces mg plus F sin theta. Okay. Right. Write down quickly. Now I'll ask a question. How many of you say that? Raise your hands. My question is, how many of you say this object moves under acceleration in the right direction? Raise your hands. How many of you say this object moves under acceleration to the right direction? Raise your hands. How many of you say this object moves under acceleration to the right direction? Raise your hands. How many of you say this object is at rest? This object is at rest. Anyone says this object moves under constant velocity? Do you think this object moves under constant velocity? Because I don't get any replies from you. Okay. Now I told you that when you consider this object, there is an external force in the horizontal direction F cos theta. We learned in Newton's first law that if there is no external force, object must be at rest. If not, object must be moving under constant velocity. But if there is an external force, I told you, object must undergo acceleration. If there is an external force, object must undergo acceleration. Then we can apply F equals mv. So because of F cos theta component, this object moves under acceleration to the right side direction. Therefore, I can apply F equals ma to the right side direction. I can apply F equals ma to the right side direction. I can apply F equals ma to the right side direction. Then, for the object, if I apply F equals ma, for the object, in the direction of motion, object is moving to the right side direction, F equals ma. Right side direction, F equals ma. External force, horizontal direction, external force is F cos theta. F cos theta. Mass of the object, simple limb. Acceleration of the object, I say simply. Acceleration, I say simply. Simply. Then in case if you want to find the acceleration, acceleration will be F cos theta over simply. Now these are not standard equations, but whenever you in a question, if you get a force inclined direction, then this is what you want to do. Okay, I think once you finish writing until here, raise your hands. Once you finish writing until there, raise your hands. Now there is no specific heading for case 5. Okay, there is no specific heading for case 5. Once you finish, raise your hands. Keep doing. Quickly. Don't worry, these things are not difficult things. When you practice, they are easy. Then case number 6. If you finish writing, please raise your hands. Then only I can discuss next section. Don't waste your time. Finish writing quickly. Okay. Now case number 6 now. So in case number 5, there was only one external force on the object. Now when it comes to case number 6, if there are two external forces acting on the object in the inclined direction, how do we find the normal reaction force? That's the goal. If there are two or more than two inclined forces acting on an object, how are we going to find the normal reaction force on the object? That's the target. Okay. Then case number 6. Now, my ground, my object. Those diagram with me. Right. Now there are two external forces acting in the inclined directions. This external force, I say F1. Angle of inclination to the horizontal, I say theta1. Theta1. This external force F2. Angle of inclination to the horizontal. Angle of inclination to the horizontal. Theta2. Theta2. If I mark other forces, weight of this object, simple mg downwards. Weight of the object, simple mg downwards. there is a contact between bottom surface of this object and the ground. Then there must be perpendicular forces acting on the object as well as ground. The normal reaction force on the object, capital R acts. The same idea. Okay, now first of all, we'll resolve this F1, F2 inclined forces into two perpendicular components, horizontal and vertical. If I resolve F1, the horizontal component will be F1 cos theta 1, F1 cos theta 1. The vertical component of F1 will be F1 sin theta 1 downwards. F1 sin theta 1, sin theta 1. Mass simple limb. If I resolve F2, the horizontal component will be F2 cos theta 2, this direction, to the left side direction, F2 cos theta 2. Downward direction, F2 sin theta 2, F2 sin theta 2. Okay, F2 sin theta 2. I think you can remember vector resolution. I think I don't need to explain why this becomes F2 cos theta 2, why it is sin theta 2. I don't need to explain. I explained it in vector section. Okay. Now, same principle. Now, this object does not move vertically upwards or downwards. Therefore, we can say this object is under vertical equilibrium. Suppose if this object is under vertical equilibrium, vertical upward forces addition must be equal to addition of vertically downward forces. If I ask you a question, how many vertical forces acting on this object? How many forces vertical? It can be forces or force components. Reply in chat box. It can be forces or force components. How many vertical forces or force components acting on the object? How many vertical forces or force components acting on the object? Reply. Now it's very easy answer. There are 4. R is 1, mg second one, F1 sin theta 1 third vertical force, F2 sin theta 2 fourth vertical force. Considering vertical equilibrium, you can write down. Considering vertical equilibrium. Considering vertical equilibrium, you can write down. Upward force R, mg, F1 sin theta, F2 sin theta downwards. Therefore, R equals normal reaction force. R equals mg plus F1 sin theta 1, F1 sin theta 1 plus F2 sin theta 2. These are standard equations now. Why I divided? Now, in the theory, there is no specific section to be taught as case 1, case 2, case 3, case 4, case 5, case 6. But why I divide into such cases and why explain? Now, there can be different question patterns asked in normal reaction forces. So, all the question patterns I give as cases. So, when it comes to theory, I only want to teach you what is normal reaction force. That's it. So in the note or anything, the theory, I don't need to teach about dividing in if there are two vertical forces, if there are inclined forces, how to find normal reaction force. There is no specific theory for that. But when we do questions, we get this type of questions. That's why in order to do the question easily, so we split into cases and we learn those concepts. These are not standard equations. These are not standard equations, not standard equations. F equals m is standard equation. You can apply F equals m directly. But this one are standard equations. And now, okay, now the next idea. Now, how many horizontal forces acting on the object? Horizontal forces. In this case, there was only one horizontal force, F cos theta. When it comes to case 6, there are two horizontal forces, F1 cos theta 1 right side direction, F2 cos theta 2 left side direction. Then the resultant. Now, for an example, I say F1 cos theta 1 force is larger than, for an example, because without knowing F1 theta 1, F2, theta 2 values, we can't tell which one is larger. F1 cos theta 1 is larger rho, F2 cos theta 2 is larger. We can't tell exactly. Without knowing these values exactly, we can't tell. F1 cos theta 1 force is larger rho, F2 cos theta 2 force is larger. We can't say. Therefore, we'll assume, if you assume F1 cos theta 1 is larger than F2 cos theta 2, if you assume, let's assume, okay, let's assume F1 cos theta 1, F1 cos theta 1 larger than F2 cos theta 2, then what is the direction of resultant force? If what is the direction of resultant horizontal force? Right direction. This one is larger. This one is like 5 Newton. F2 cos theta is like 3 Newtons. 5 Newtons, 3 Newtons. Resultant is in the right side direction, just 2 Newtons. Then we can apply F equals mv. Because there's a resultant force acting on the object right side direction. Whenever there is a resultant force, object must undergo acceleration. Therefore, I can apply to the object F equals mv. Right side direction F equals mv. Then F1 cos theta 1 minus F2 cos theta 2. F1 cos theta 1 minus F2 cos theta 2. This is the resultant force. I hope you understand. Then mass simple limb. Acceleration, I say simply. Acceleration, I say simply. Acceleration, simply. Acceleration, it's a simply. Simply acceleration. In case if you want to find the acceleration, you can subject A. Simply equals F1 cos theta 1 minus F2 cos theta 2 over simply. Now, raise your hands, how many of you understood case number 5 and 6 answer? Understood case number 5 and 6 answer? Understood? Okay. Once you finish writing, raise your hands. Once you finish writing, raise your hands. Now you will get, I think, now I post the tudes on tomorrow. I post the tudes tomorrow. Then you will see the tudes also. Quickly. Once you finish writing, raise your hands. Okay. Quickly. Then sample question 1. Then sample question 1. Finished writing? We'll take a break at now 7:30, 8:30, 9:30. So we'll take a break at 9:30. Finished writing? If you finished writing, please raise your hands. Hands up, still writing hands. How many of you still writing? Raise your hands. Quickly. Quick. Now, sample question SQ1. Sample question 1, SQ1. Write down, find normal reaction and acceleration of below objects. Sample question, write down. Find normal reaction force and acceleration of below objects. Find normal reaction force and acceleration of below objects. First one. Find the answers. Now you want to find the normal reaction and acceleration. Mass of this object, I say 5 kilograms. 5 kilogram mass. And external force, let's say external force, I say 10 newtons. 10 newtons. Angle of inclination 30 to the horizontal. This angle is 30. This angle 30. Then you want to find the normal reaction force acting on the object and the acceleration. That is first example. Then example number 2, once you found normal reaction and acceleration for example 1, example number 2, 10 kilogram mass. There are two forces, inclined forces. There are two inclined forces. 20 newtons. This inclined force, I say 10 newtons. Angles are 60. Angles are 60. This angle is 60. This angle is 30. This angle is 30. 60 and 30. Find the answers. Now, very similar idea. If you understood case 5 and case 6, you can easily find the normal reaction force acting on the objects and you can find the acceleration of the objects. Find them now. Once you found, raise your hands. Then I will give some time. I will give 5 minute time. 5 minutes is enough. I will give 5 minute time. Then I'll start explaining. Keep on doing. Once you found the answer, once you got the answers, raise your hands. I will give 5 minutes.
Finish doing. Raise your hands once you found the answers. Once you found the answers. Still doing answer. Still doing. Keep on doing. Keep on doing. First one finished answer. First one finished. First one finished answer. Okay, then many finished. Therefore, I start explaining first one. You keep on doing second one. I'll explain first one. Then normally, whenever you got a question with inclined forces, normally what we do, we resolve the inclined force. First of all, what we do, we incline, resolve force, and then only we start doing the question. Now, now we want to find the normal reacting force. So always understand, mark all the forces acting on the object. Very important. First of all, resolve this inclined force into perpendicular directions, horizontal and vertical, and then mark all the forces, because when you miss one force, entire answer is wrong. So therefore, mark all the forces acting on the object. Now, up to now, you learned two forces, weight and normal reaction. Okay. If I mark the forces, weight mg, how much? Mg means mass into acceleration. Gravitational acceleration is 10. Then weight, we know weight is 50. Am I correct? Mg 5 into 10. 500 means 50. Weight is 50 newtons. If 50 newtons, normal reaction force capital R. Resolve 10 newton to two perpendicular components. Horizontal component will be 10 cos 30. Horizontal component 10 cos 30. Vertical component 10 sin 30. Vertical component 10 sin 30. Vertical component 10 sin 30. Mass 5 kilograms. Okay. Now, if you consider vertical equilibrium, vertical equilibrium, vertical equilibrium, we can write down capital R. Capital R must be equal to, upward force must be equal to 50 plus 10 sin 30. Am I correct? Downward forces are 50, 10 sin 30. 50 plus 10 sin 30. What is the value of sin 30? Value of sin 30 is half. 50 plus 10. Sin 30 means half. Sin 30 means half. That means 50, 10 over 2 means 5. 10 over 2 means 5. 55. Capital R. Normal reaction force acting on the object is 55 newtons. Normal reaction force acting on the object is 55 newtons. Newton is mass. Newtons. And also we want to find the acceleration of the object. Acceleration of the object. How can we find the acceleration? Apply F equals ma. This object is accelerating to the horizontal direction because of 10 cos 30 external force. Therefore, apply F equals ma in that direction. Acceleration, I say simple A. This object is accelerating to the right side direction because of the external force 10 cos 30. Apply F equals ma in the direction of motion. Apply F equals ma in the direction of motion. F equals ma. Then what is the resultant horizontal force acting on the object? Only 10 cos 30. Only 10 cos 30. Only 10 cos 30. 10 cos 30 must be equal to mass of the object is 5 kilograms. Acceleration, I want to find acceleration simply. Then simple A must be equal to, here 5, here it's 2. I can divide this 10 by 5. 1, it's 2. 2 cos 30 means 2 cos 30 means root 3 over 2. 2 cancel out. Cos 30 means root 3 over 2. 2 cancel out. Root 3 means you know that 1.732 m is minus 2. Now you can keep your answer as 1.73 because usually we keep our answers up to 2 decimals. Then acceleration is equals to 1.73, 1.732. Hands up, how many of you got these two answers? R55, acceleration 1.73 answer. It's not difficult. It's not difficult, right? You got the answers. Then I will do this question also.
Now, in this case, you know that in this case, same idea. Resolve the forces. When you resolve it, what is your horizontal component of 20 Newton? 20 cos 60. 20 cos 60. When you resolve this one into vertical component will be 20 sin 60. 20 sin 60. Resolve this 10 Newton. Left side direction horizontal component is 10 cos 30. Downward direction 10 sin 30. Downward direction 10 sin 30. 10 sin 30. Then vertical equilibrium. Vertical equilibrium mark the forces. Weight mg. Mass 10 kilograms, G10, mg 100. Normal reaction is R, upwards. Normal reaction upwards, weight mg downwards. And now you can say vertical equilibrium. Consider vertical equilibrium. You can consider vertical equilibrium. Vertical equilibrium, you can write down. R must be equal to downward forces, 100 downwards, plus 20 sin 60 downwards. 20 sin 60 downwards plus 10 sin 30 also downwards. 10 sin 30 also downwards. 10 sin 30. 10 sin 30 also downwards. And then R equals 100 plus 20 sin 60 means root 3 over 2 plus 10 sin 30 means 10 sin 30 means half. Again R equals 100 plus now 20 root 3 over 2. I can divide by 2, then it's 10. 10 root 3. 10 root 3 plus 10 by 2 means 5. Then root 3 means it's 1.732. 100 plus root 3 means understand 1.732 plus 5. Now remember now, please, if it's better if you can remember now. Normally, so when you do calculations, most of the calculations, sometimes your final answer will end up with root 2 values, root 3 values. Okay. Now remember, root 2 is always remember, learn by heart these things. Then it's better you can quickly finish simplifications. Remember, root 2 means always 1.414. Learn by heart. Root 3 means 1.732. 1.732. You learn by heart these two values, then easy. Then finally we are ending with 100. 100 plus 505 plus 17.32. 105 plus 17.32 means how much? 122.32 newtons. Hands up. Who got 122.32? Hands up. Got this answer? Got this answer. How many of you got this answer? R as 122.32 newtons. Hands up. Got this answer. How many of you understood this one? Understood. R is this value. Understood, hands up. Understood. I understood this value. I understood. Understood, hands up. Understood, hands up. Understood, hands up. Okay. Then what we can do? Now I want to find the acceleration. If you want to find the acceleration, now why do we want to subtract now? Because understand 20 sin 60 downwards, 10 sin 30 also downwards. Then very simple idea, right? It's not difficult. Just think the idea. If you consider vertical equilibrium, these two forces acting downwards, weight acting downwards, only R is acting upwards. Then I taught you that the addition of all the downward forces must be equal to the upward force R. Weight downwards 100. This one 20 sin 60 downwards, 10 sin 30 downwards. Adding them equals to R. It's not difficult, right?
Today we can do two questions. Today we can. Then acceleration. When it comes to acceleration, then this is right side, 20 cos 60 right side, 10 cos 30 left side. In that case, yeah, there's a minus in that case. If I erase and if I find the acceleration. Then F equals ma. To the object, applying F equals ma right side direction. Right side direction F equals ma. Right side direction F equals ma. Resultant force. How many horizontal forces acting on the object? There are two. 20 cos 60 right side direction, 10 cos 30 left side direction, 10 cos 30 left side direction. Then I consider right side as positive. Right side as positive. Then 20 cos 60 positive, 10 cos 30 negative. Then I can write down 20 cos 60 minus 20 cos 60 minus left side, 10 cos 30 left side, therefore minus 10 cos 30 must be equal to mass is 10 kilograms. I want to find the acceleration simply. Acceleration simple A. Simplification. 20 cos 60 means half minus 10 cos 30 means root 3 over 2. Cos 30 root 3 over 2. 10 simple A. Then I can say 20 over 2 means 10 minus here 5 root 3. 5 root 3 10 A. Right? Then 10 minus 5 root 3 means how much? 5 root 3 means 1.73. You can stop 73. Okay, we'll stop at 1.73. If you want, you can write down 1.732 and you can simplify. Okay, we'll stop at 1.73. And then when you multiply 1.73 into 5, 1.73 into 5, how much? 15. 5 into 7 means 35 plus 1, 36. 8.65. 10 minus 8.65 equals 10 simply. 10 simply. 10 simply. Then 10 minus 8.65 means 1.35 over 10 simply. Am I correct? Therefore, acceleration of the object to the right side direction 0.135 ms minus 2. This is the answer. Hands up, who got this answer? How many of you got this answer? Raise your hands. How many of you got this answer? Okay. Then case, I think we discussed case 1, case 2, case 3, case 4, case 5, case 6 also discussed now. When it comes to weight force, we didn't learn much about weight force. But normal reaction force, yeah, there are lots of things to learn regarding normal reaction forces. Okay. I think you got the idea. You got the idea. Okay. Now we'll put case number yes, case 6. Now we'll put okay, case number 7. Put case number 7. Put case number 7. Right. Now we'll write down a small topic for case number 7. We'll write a small topic for case number 7. Write down. When objects are in contact with each other and when two objects are in contact with each other and when two objects are in contact with each other and if capital F external force is applied, if capital F external force is applied, okay, that's the topic. Now this is important because mostly you can find MCQs under this idea. You can find MCQs under this idea.
So when you check your past papers. Okay. Now, next case number 7. Okay. Okay. Case number 7. Case number 7. Now there are two objects in contact with each other with different masses, so same mass. So if there are two objects in contact with each other, and when you apply an external force on one of the objects, something in this way, this is your ground, this is your ground. There are two objects. First object, and there is another object. Second object. The ground. Now I say mass of the first object, let's say simple capital M. Mass of the first object, capital M. Capital M mass. Mass of the second object, simple M. Simple M. Now, if an external force applied on capital M mass, right side direction. Capital F external force applied to the horizontal direction on capital M mass, right side direction. Okay. I'll ask a question. Now, listen to my question very clearly. Now, in this case, how many normal reaction forces acting on capital M? Once again, I repeat the question. How many normal reaction forces? How many normal? I'm not asking how many forces acting on capital M. I'm asking how many normal reaction forces acting on capital M? How many normal reaction forces acting on capital M? Any answer? How many normal reaction forces acting on capital M? Because we know, you know what is normal reaction? Whenever there is a contact between two surfaces, the type of force generated is what we call as normal reaction. Whenever there's a contact between two surfaces, type of force generated, that's what we call as normal reaction. Then we know that this object, capital M, is in contact with the ground. Definitely, there's a normal reaction. Okay. So if I mark the weight mg downwards, weight capital Mg downwards, this object is in contact with the ground. Therefore, there will be a normal reaction force on capital M upwards. I say R1. I say R1. Normal reaction force. What is R1? Mark down. R1 is normal reaction force on capital M. This is on capital M. On capital M by ground. By ground. By ground. And also now by providing an external force, if I try to move capital M, what would happen? This capital M will compress simple M. This capital M compresses simple M. When capital M compresses simple M, there's a contact between surfaces. As a result, capital M produces a force on simple M right side direction perpendicular to the surface. That is normal reaction force on simple M. I say capital R. Normal reaction force. Write down. When you're writing, normal reaction force on capital M by ground. This is what? When capital M compresses simple M, capital M produces a force on simple M, right side direction, perpendicular to the surface. Normal reaction force on simple M by capital M. Every reaction has equal opposite reaction. Simple M also compresses capital M to the left side direction. This is also normal reaction. What is this capital R? This capital R is, I don't have space. So I write here. Okay, I write here. normal reaction force on capital M by simple M. Then there are two normal reaction forces acting on capital M, and also there are two normal reaction forces acting on simple M. If I mark the weight simple mg downwards, normal reaction force on simple M by the ground R2. On simple M by ground. Write on all the important things. Okay. Now this is important. This case number 7 is very important because MCQs are coming from this section. Very important. Okay. And then we understood how many total forces acting on capital M. How many total forces acting on capital M? If R, mg, R1, there are 4 forces acting on capital M. How many total number of forces acting on simple M? R, mg, R1, there are 3 forces. If I ask you how many vertical forces acting on capital M, there are 2 vertical forces, capital mg downwards, R1 upwards. How many vertical forces acting on simple M? Simple mg downwards, R2 upwards, there are 2. If I ask you how many horizontal forces acting on capital M, F right side, R left side. How many horizontal forces acting on simple M? Only R. Okay. Now shall we mark the forces? If you consider only capital M, if we mark the forces on capital M, okay. If we mark the forces on only on capital M, forces on capital M mass, and draw capital M mass, capital M mass, capital mg, R1 upwards, capital F right side, and R left side. R left side, there are 4 forces. And draw this diagram also. There are 4 forces acting on capital M. If you mark the forces on simple M, forces on simple M, there are 3 forces. R left side, R right side, simple mg downwards, R2 upwards. Once you finish writing, raise your hands. Once you finish writing, raise your hands. Once you finish writing, raise your hands. Quickly. If you finish, raise your hands. Right, okay. Okay.
Now, first important thing is okay. Now, now you understood when there are two objects in contact with each other. We understood how forces exert on each object. We understood separately. We drew each object. We mark the forces on capital limb and simple limb. You understood. Now, important thing you need to note is understand. Now, we are not talking anything about frictional forces. Still, we can't learn about frictional forces because frictional force is the last force that you will learn after tension forces, compression forces. Friction force will be the last type of force you will learn. Therefore, we don't consider any frictional forces acting on the object by the ground action. Okay, we assume all the cases, we assume the ground is very smooth. Okay, so we don't think about frictional forces. In that case, understand, very carefully listen, this is very important point. Because of this external force, when you consider entire system, first important point is understand, just think about this entire system. When you think about entire system, now very carefully answer for my question, keep your 100% focus, that's important. Now I am considering entire system, that means capital limb and simple limb both as one system. If you consider entire system as one object, how many horizontal forces acting on the system? Very carefully go through the diagram until when you consider capital limb and simple limb as your entire one system, how many horizontal forces acting on the system? If I separately ask you how many horizontal forces acting on capital limb, yes, you will tell 1 and 2. There are 2 horizontal forces acting on capital limb. If I ask you separately how many horizontal forces acting on simple limb, there is only 1. You will say like that. If you consider entire system as 1, how many horizontal forces acting on the system? Any answer? How many horizontal forces acting on your system? Any answer? There is only 1. There is 1, right? Some people say there are 3 horizontal forces acting on the entire system. That's wrong. The reason is, now why they say there are 3 horizontal forces acting on the system? The reason is, if first one, these are second force, these are third force. That's wrong. When you consider this system as a one system, capital limb and simple limb as a one system, what would happen for this R and that R? They get cancelled out. They get cancelled out. Okay, the result is 0. You are considering entire system as one system. This are cancelled out. Then entire system, there is only one horizontal force, that is capital F. That is first important thing. Write down red color pen important. Red color pen important, write down. Important. When considering capital limb mass separately, there are 2 horizontal forces. There are 2 horizontal forces acting on capital limb. So when you're writing, understand, write on. There are 2 horizontal forces acting on capital limb. Okay. So the same point continue. When considering simple M separately, comma, when considering simple M separately, there is one horizontal force. There is one horizontal force acting on simple limb. There is one horizontal force acting on simple limb. Okay, super red color pen, write down. Next point, super red color pen. When capital limb and simple limb are considered as a one system, when capital limb and simple limb are considered as a one system, when capital limb and simple limb are considered as a one system, comma, there is only one horizontal force. There is only one horizontal force there is only one horizontal force, that is capital F. That is capital F. That is capital F. Okay. Inside the bracket, write down capital R, write down normal reaction, write down, right inside the bracket, write down normal reaction on capital limb and simple limb. Normal reaction forces on capital limb and simple limb get cancel out. Normal reaction forces on capital limb and simple limb get cancel out. Normal reaction forces on capital limb and simple limb get cancel out. Close the bracket. Okay. That is first important thing. If I ask you separately, what is the resultant vertical force on capital limb? What is the answer? What is the resultant vertical force on capital limb? Any answer? What is the resultant vertical force on capital limb? What is the resultant vertical force on capital limb? 0. Why? Because there are only two vertical forces on capital limb. Capital mg downwards, r1 upwards. Then you know that r1 must be equal to, if this object is not moving upwards, if this object is under vertical equilibrium, you know r1 must be equal to capital mg downwards. Right? Therefore, resultant vertical force. Resultant vertical, I'm talking about resultant vertical force. Resultant vertical force on capital M is 0. And when you think about simple limb, again there are two vertical forces, R2 and simple mg. If this object is not moving vertically upwards, this object is under vertical equilibrium, therefore R2 must be equal to mg. Then what is the vertical resultant force on simple limb? 0. If I ask you what is the resultant vertical force on the system, that is definitely 0. Okay. Next point, write down. Blue color, it's not that much important. You know this idea. In blue color, write down. If capital limb and simple limb objects, are in vertical equilibrium, suppose if they are in vertical equilibrium only, okay. If capital limb and simple limb objects are in vertical equilibrium, comma, the resultant vertical force on capital M and simple limb. The resultant vertical force on capital M and simple limb must be 0. Now we are talking about very serious section, okay? Force is very important. Force is very, very important. I don't know. It's really important section. The resultant vertical force on capital limb and simple limb must be 0. I take time and I explain. Okay. Now what you do, write down, under that write down, considering vertical equilibrium of capital limb. Write down this one. Considering, no one explains to this level, I know that. Considering vertical equilibrium of capital limb. Then write down R1 must be equal to what? R1 must be equal to capital mg. Considering vertical equilibrium of simple limb. Considering vertical equilibrium. Considering vertical equilibrium of simple limb. Then you know that R2 must be equal to mg. Then you know that R2 must be equal to simple limb g. Okay. Now we are learning everything from step by step. Okay. So get the maximum benefit. Okay. Right. Next important thing is, okay, now capital limb and simple limb both are in contact with each other. Now when we apply capital F external force, the entire one system, if you take the capital limb and simple limb as one system, there is only one resultant force, capital F, right side direction. Definitely what happens? System must undergo acceleration. Because when you take about capital limb and simple limb as one system, when you apply a force, this entire system moves. Just think now, if there are two blocks and when you apply a force on this block,
And when you try to move this block also moves together with this block. Both the blocks are moving together. You understand what I'm saying? Now, when you apply external force and when you try to move this block also moves forward direction. Now, we know there must be an acceleration to the system. There must be an acceleration. Now, my question is now we understood when we provide an external force capital F, the system must accelerate. We understand that idea. System must accelerate. We understand that idea. But my question is, do you think, how many of you think that acceleration of capital M and acceleration of simple M are equal hands? By providing capital F force when the system moves, raise your hands. How many of you say acceleration of capital M and acceleration of simple M are equal hands? Acceleration of capital M and acceleration of simple M are equal hands up. They are equal. They are not equal hands up. They are not equal hands up. They are not equal. They are equal. Okay, they are equal, right? They are equal. Okay, they are equal. Because if the system moves together, until system moves together, understand acceleration of capital M, no matter their masses are different, be to that external force capital F, if the entire system moves together, acceleration of capital M and acceleration of simple M, they must be equal. Red color pen important, write down. Red color pen important, write down. Red color pen important, write down. If the system inside the bracket capital M and simple M, close the bracket. If the system inside the bracket capital M and simple M, close the bracket. If the system inside the bracket capital M and simple M, close the bracket, moves together. If the system moves, that means capital M and simple M moves together. Okay. If capital M and simple M moves together under capital F external force, under capital F external force, under capital F external force, comma, 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 the acceleration of capital M and acceleration of simple M must be equal. The acceleration of capital M and acceleration of simple M must be equal. Acceleration of capital M and acceleration of simple M must be equal. Then the system moves under same acceleration. System moves under same acceleration. Acceleration of capital M also is A. Acceleration of simple M also A. Now what we can do, we can apply F equals ma separate. Now there are three possible ways applying F equals ma. You can apply F equals ma only considering capital M mass, same acceleration A. You can apply F equals ma considering simple M mass. If not, you can do one more thing, important thing. You can take entire system as 1 and you can apply F equals ma. So I will give some time. 2 minutes. Try to apply F equals ma considering forces, horizontal forces on capital M. Apply F equals ma. And considering only forces on simple M, apply F equals m. Then considering both capital M and simple M as one system and apply F equals m. I will give 1-2 minutes, then I'll explain. Then we can do sample question and we can finish doing this case also. I will give 2 minutes. Do it quickly. Do it quickly.
Raise your hands. How many of you applied F equals ME? Raise your hands. Applied F equals ME, hands up. Now, this is important. Now, normally in forces questions, you know what is critical? When you're doing forces questions, the most critical thing is deciding the forces. What are the forces acting on that object for the relevant scenario? That is the really difficult problem. Because they give a nice story. By reading the story, understand what are the forces acting on the object. That is really critical. So if you forget to apply, if you forget to mark one force, if you forgot now, let's say there are 5 forces acting on that object. In case if you forget to mark one force, your entire diagram is wrong. When your entire diagram is wrong, your entire calculation, because you know that now. Forget about this R. When you apply F equals ME, that entire question is wrong. So therefore, most critical part in F equals MA question is deciding the forces acting on that object relevant to that scenario. That is the difficult thing. Then next difficult thing is applying F equals ME. Applying F equals ME is next difficult thing. Once you applied F equals ME, by understanding the forces acting on the object, the remaining can be easily done as a smooth flow. Remaining is simplification. Okay. Now this is important. You must practice for this. Okay. We'll take a break at 9:15. Okay. Right. Now what we can do now? Now I consider only capital limit. I try to apply F equals ME. Let's consider capital lim. If I consider capital lim and if I consider capital lim, if I apply F equals ME on capital lim, applying F equals ME on capital lim, because the entire system is moving to the right side direction under simply acceleration. Right side direction. If I apply F equals ME, if I apply F equals ME on capital lim, F equals ME on capital lim, resultant force on capital lim. Then first of all, you should mark the forces on capital lim. Then we understood there are only 2 horizontal forces on capital lim. You apply to the right side direction F equals ME. Then right side direction forces are positive, left side direction forces are negative. Then what is the resultant force acting on capital lim? F minus R. Resultant force acting on capital lim is F minus R. F minus R. Capital F minus R must be equal to mass of capital lim. Capital lim. Acceleration is same acceleration simply. Equation 1. Equation 1. Right? Now, if I ask you to apply F equals MA on simple limb mass, if you apply F equals MA on simple limb mass, right side direction, we apply always F equals MA in the direction of motion, right side direction, F equals MA. Then there is only one horizontal force on simple limb, capital R right side, capital R right side. R equals only one horizontal force on simple limb. You want to only consider forces on simple limb. R right side, R only one horizontal force. We don't consider vertical force. Okay, we are applying F equals MA to the right side direction, horizontal direction. One R, mass simple limb, acceleration simply. Second equation. And next thing is important. Normally, what we do in order to find the acceleration of a system. Now, normally these type of questions, what we do, first we find the acceleration of the system. So therefore, we apply F equals MA for the entire system, for the system, applying F equals MA in the direction of motion, applying F equals MA in the direction of motion. Now, I told you, when you consider entire system, there is only one force, because this R and that R cancel out. Then there is only one horizontal force, that is capital F. That is capital F. Capital F. Now, what is simple limb here? Yes, simple limb means understand mass of the entire system. Mass of the entire system means capital M plus simple limb. Capital M plus simple limb. Acceleration system is simple limb. Raise your hands. How many of you applied in this way? How many of you applied capital limb, simple limb, entire system? These 3 equations answer. If you understood this idea, that's it. Hands up who got these three equations. Hands up who got these three equations. Okay, that's it. Then good. And then once you finish writing until here, we can do some questions. We'll do questions. Okay. Right. Okay. If you finish writing, hands up. Finish writing until hands up. Finish writing until hands up. Finish writing. Okay. Now sample question, write down. Find the acceleration. Sample question. Find the acceleration of the below system and the normal reaction forces on the system. Find the acceleration and normal reaction forces acting on below system. Find acceleration and normal reaction forces acting on below system. Now be very careful. This time there are three masses. There are three masses in contact with each other this time. There are three masses in contact with each other. There are three masses. Be very careful. There are three masses in contact with each other. This is not difficult, right? Just don't you think it's difficult? There are three masses. There are three masses. Bruce diagram. First mass. Second mass. Third mass. In contact with each other, there are three masses. Right? Masses are 15, 10, 5. Let's say this mass is M1 15 kilograms. M1 15 kilograms. This is M2 5 kilograms. M3 10 kilograms. There are three masses now. Now I applied external force 400 Newton on M1. I applied 400 Newton on M1. My external force 400 Newtons, capitally 400. Okay. Find the answers. Find the answers. Now, please, when you mark the normal reaction force notations, okay, follow this way. I will guide you, okay. Now think wisely the forces on simple M1. Now think wisely how many forces on simple M1. Already F is acting on simple M. Weight, weight. Weight is M1G, if not 15 into 10, 15 into 150 Newtons. 150 Newtons. M1G, if not 150 Newtons. 150 Newtons. Normal reaction force, let's say R1. R1. And you know that M1, M2 in contact with each other due to capital F external force. M1 compresses M2, M2 compresses M1. Therefore, there are normal reaction forces. Let's mark the mass. Let's mark the mass R4, R4. Let's mark normal reaction force on M1, R4. Understand, is perpendicular. Normal reaction force on M2, R4. They are perpendicular. And then there are four forces, R4, 150, R1, 400. And when you think about M2 mass, weight, yes, weight M2G, if not 5 into 10, 50, 50, 50, 50 Newtons. 50 Newtons, I don't know, you can see this one, 50 Newtons, okay, 50 Newtons. R, normal reaction force is R2, R2.
There's a contact between M2 and M3. M2 compresses M3, M3 compresses M2. Normal reaction forces, let's say R5, R5. Normal reaction forces, let's say R5, R5. R5 perpendicular, R5. Then weight M3G, that means 100. 100. Normal reaction, it's R. Now, raise your hands. How many of you understood the forces marked on these masses answer? How many of you understood how I mark the force answer? You guys understood answer? I think you guys understand, right? And now I will give some time. I will give some time. Now my advice. Now there is some kind of pattern of doing these type of questions. Now the idea is very simple. First, you want to mark the forces on each mass. You want to mark the forces, all the forces on each mass. I think I have marked all the forces acting on all the masses. Then basically you want to apply F equals ME. You want to apply F equals ME. You can apply F equals ME for 15 kilogram mass or 5 kilograms, sometimes 10 kilograms. Now, what's your target? In the question, they asked you to find acceleration simple A. Therefore, simple A acceleration is unknown. But you know, entire system moves under same acceleration. Acceleration of simple M1, simple M2, simple M3, all are same acceleration. You want to find simple A. Not only you want to find simple A, you want to find R1 because they ask you to find normal reaction forces acting on the system. R1, R2, R3, R4, R5. You can find R1, R2, R3 easily considering vertical equilibrium of each mass. If you think about separately simple M1, considering vertical equilibrium of simple M1, R1 equals 150. You can find R1, R2, R3 easily. There is no issue with finding R1, R2, R3. The problem is somewhat complex. The problem is finding simple acceleration R4, R5. That is problem. So advise you, once you found R1, R2, R3, my advice is take entire system as one system. Take entire 15, 5, 10 as one system and apply F equals ME. Then find acceleration. Follow what I'm saying. Take this as one system, apply F equals ME, find simply acceleration. Once you found the acceleration, then separately apply F equals ME. Separately apply F equals ME on this mass or this mass or that mass. You can find R for one R. I think I instructed you well. I will give some time. Now, always follow my instruction. Once you got the answer, it's completely all right. It's a right answer, wrong answer. That doesn't matter. All trying is matter. Once you got the answer, please be humble to raise your hands. Okay. Once you got the answer, be humble, raise your hands. Then only I can discuss next section. I'll give some time, do it.
Once you got the answer, raise your hands. If you got the answers, raise your hands. I'll give you some time. Now we are going to finish normal reaction forces. Then we are talking about tension forces as well. Finished? Right, I'll start explaining. Okay, I give you some time because the problem is can't give that much of time. That's the problem. I wish I can give some more time. Okay. Now my target is to find normal reaction forces and acceleration. Now we know this system does not move upwards, right? Therefore, the system is under vertical equilibrium. If I consider vertical equilibrium, considering vertical equilibrium, considering vertical equilibrium, considering vertical equilibrium, what can I do? If I consider simple M1, that is 15 kilogram mass. If I consider vertical equilibrium, I know that R1 upward, there are only two vertical forces. How many forces on simple M1, 15 kilogram? There are 1, 2, 3, 4 forces, but there are only two vertical forces, R1 upwards, 150, weight downwards. Therefore, I can write down R1. R1 must be equal to 150 newtons, easy. 150 newtons. I found one normal reaction force, R1. If I consider 5 kilograms, then there are only two vertical forces on 5 kilogram also. R2 must be equal to 50. R2 must be equal to 50. R2 must be equal to 50. R2 must be equal to 50 newtons. Okay, when you consider 10 kilogram mass only, just think about only 10 kilogram mass, there are three forces, 100, R3, R5. Vertical equilibrium, if I consider vertical equilibrium,
R3 upwards must be equal to 100 downwards. 10 kilograms. 10 kilograms R3. R3 must be equal to 100. That is fine. I think all of you can do that one. And next thing is, I'm going to apply now. Now, still I want to find R4, R5A. If I found R4, R5A, then problem solved. System. My advice is apply for the system F equals MA and try to find A. Then easy. I'm going to apply for the system, entire system. Entire system. I'm going to apply in the direction of motion. Right side direction, I'm going to apply F equals MA. Right side direction, I'm going to apply F equals MA. Then force F. Then what is the resultant horizontal? If I take this as one system, what is the resultant force? Resultant horizontal force? Resultant horizontal force will be R4 cancel out, R5 cancel out, and there is only one horizontal force, that is 400. 400. Total mass of the system. Total mass of the system is 15 plus 5 plus 10 into acceleration of the entire system. Simply. Finally, simple A will be equal to 400 over 15 plus 5, it's 20, 15 plus 5, 20, 20 plus 10 means 30. 400 over 30 means 40 over 3. 40 over 3. Right? 40 over 3 means how much? 40 over 3 means 13.33 m is minus 2 acceleration. This is the acceleration system. Once you found the acceleration, now you want to find R4, R5. You want to find R4, R5. Okay. Now, first of all, okay, now you can find R4 first and you can find R5 later. Now I thought of finding R5 first. I'll ask the question. Now, you know, in order to find R5, you want to apply F equals MA4 because R5 is involved with M2 5 kilograms and M3 10 kilograms. R5 involved with M2 5 kilograms and M3 10 kilograms. I'll ask a question. In order to find R5, if you have, for which mass, if you apply F equals MA, it is best. Now you want to apply F equals MA for M2 mass or M3 mass. What is the best mass to find what is the best mass to find R5? When you want to apply F equals MA, what is the best mass? If you consider which mass, you will be able to find R5 quickly. Anyone? 10 kilograms. Because the problem is, now, you can't apply F equals MA. You can apply F equals MA. The problem is, you don't know R5 and you don't know R4. So therefore, when you apply F equals MA, there are two unknowns in one equation. It's a problem. But when you apply F equals MA for M3, 10 kilogram mass, there is only one force. You know mass, you know acceleration. Therefore, it's best to apply F equals MA for M3 mass in order to find R5. Therefore, I consider 10 kilogram mass. I'm going to apply F equals MA for 10 kilogram mass in the direction of motion. F equals MA. Then there is only one force, that is R5. Only horizontal force is R5. Must be equal to mass of M3. 10. Acceleration I found that is 13.33. You can substitute 13.33. 13.33, you'll end up with 133.3 newtons. That is your R5. Hands up, who got this value? Hands up. A very similar value. Who got this value? Hands up. Anyone? Yes, most of you got this answer. Then good. Then you understand And now you can find R4. Now you can consider M2 mass and you can apply F equals MA and you can find R4. If not, you can consider M1 and you can apply F equals MA. That's no issue. Okay, I will consider M2 mass and I apply F equals MA. Then if not, I'll consider M1 mass and I'll apply F equals MA. Okay, M1 mass. 15 kilogram mass, I'm applying F equals MA. If I consider 15 kilogram mass, M1, if I apply F equals MA in the direction of motion, F equals MA, then there are two horizontal forces, 400 minus R4. 400 minus R4 must be equal to 15 kilograms into acceleration. Acceleration, I found how much? Acceleration is how much? 40/3 actually. Now, rather than now, you know what? It's completely all right to substitute 13.33 here, but it would be better if you can substitute 40/3. Then you can avoid having small deviation with your final answer. So you can substitute 13.33 and you can get the R for well, it's completely all right. But I thought of substituting 40/3 here. Then it will be better. I will get a much accurate answer. I'm substituting 40/3. 40/3. In that case, here it's 1, here it's 5. 5 into 40. 5 into 40 means how much? 200. 5 into 40 means here it's 200. Here 400 minus R4. Then my R4 will be R4 will be 200 newtons. That's it. It's very clearly understood, right? Understood. Okay, now 9:15. 9:15. We'll raise your hands. How many of you want a break right now, or we'll take a break at 9:30? How many of you going with taking a break right now? 9:15 now. We'll take a break at 9:30 or 9:15. How many of you going with 9:15 answer? 9:15, we'll take a break. We'll take a break. Okay, we'll take a break. How long you need? Reply. How long do you need? Reply. Everyone reply. How long do you need? How long do you need? Reply. Reply. How long do you need? Reply. Reply, everyone. Reply, everyone. So we'll take now 15-minute break, and again we'll do 1 hour. Then 9 will come at 9:30. 9:30 to 10:30. I don't know at what time I'll finish. 10:30 or 10:45. Okay. Yeah, we'll take 15-minute break. 15-minute break. Take 15-minute break. Come at 9:30. Come at 9:30.
Right. Okay. Right. I think we took the break. Right. Then you understood this idea also. Case number 7 we discussed. Now you have the idea about case number 7. Now we'll go with case number 7. Now, yes. Right. Case number 8. Case number 8. Case number 8. Write down. When objects are on top of each other, write down. When objects are on top of each other and the system is at rest. When objects are on top of each other and the system is at rest. Now listen very carefully. Now, if there are objects, can be 2 or 3 or more than 2 objects, are on top of each other, and if the system is at rest, how to find the normal reaction forces? That's the idea. Okay. Now I will consider 3 masses which are placed on top of each other on the ground. 3 masses which are placed on top of each other on the ground. Case number, I think 8-1. Case number 8. I think 8-1. Case number 8. Okay. Case number 8. Case number 8. Case number 8-1. Now I draw 3 objects on top of each other. My ground. This is my ground. First object. A second object. First object, second object. And then third object. And then third object. A system is at rest. Let's say mass of the bottommost object is M3, M1, M2, M3. In this case, M1 mass, M2, this mass, M3. Shall we mark the force? Now, I will start marking forces from M1 to M3. If I consider M1 mass, weight force M1G downwards. Weight force M1G downwards. M1 in contact with M2, normal reaction force on M1 upwards R1. Normal reaction force on M2 R1, action reaction forces. Okay. This R1 is on M2, this R1 is on M1. I think you understand. If I consider forces on M2, weight M2G, normal reaction force on M2, let's say R2, normal reaction force on M1, reaction force, normal reaction force on M1, reaction force R2. I think you understand. If you don't understand, put a reply in the chat box. Weight force M3G, normal reaction force R3, normal reaction force on the ground also R3, but I don't mark the normal reaction force on the ground. It's not important that much. Okay. Now, if you consider equivalent, the system is at rest, then M1, M2, M3, all the mass are at rest. If I consider equilibrium of simple M1, considering equilibrium of simple M1, considering equilibrium of simple M1. Now there are 2 forces on simple M1, R1 upwards, M1G downwards. Therefore, I can write down R1 must be equal to M1G. Anyone can understand this idea. Now, when you consider equilibrium of simple M2, you need to understand how many forces on simple M2, R2 upwards,
R1 downwards, M2G downwards. There are 3 forces on M2. Considering equilibrium of M2. Considering equilibrium of M2. Right? Then I can say R2. R2 must be equal to, there are 2 down forces, M2G, R1. M2G plus R1. What is my R1? From equation 1, R1 means M1G. Therefore, R2 equals M2G plus M1G. That means R2 equals M1 plus M2G. M1 plus M2G. You can understand, right? So when I consider the equilibrium of M3, considering equilibrium of M3, considering equilibrium of M3, then what can I do? Again, there are 3 forces on M3. Always consider how many forces on the relevant object. For M3, there are 3 forces, R2 downwards, M3G, R3. Always think about how many forces on the relevant mass. Now my relevant mass is M3, there are 3 forces. R3 must be equal to M3G downwards plus R2 plus R2 plus R2. Now you know what is R2? R2 means we know from equation 2. From equation 2, you know R2. From equation 2, this is from equation 1. R3 equals M3G plus R2 means how much? R2 means M1 plus M2G. M1 plus M2G, that means M1 plus M2 plus M3G. That is another type of idea. Now I'm talking about all the possible cases in normal reaction. Okay, normal reaction force is a wide force. Okay, so many questions they can give the normal reaction force a different way. Right? Finish writing. Raise your hands. Finish writing. Raise your hands. Raise your hands. If you finish, raise your hands. If you finish, raise your hands. Now always try to keep your focus until class finishes. Now I started at 7:30. So now I gave a break at 9:50. Then 7:30, 8:30 means 1 hour 45 minutes. I did the class. We took a break. Now it's roughly 9:30. We'll do the class until 11 o'clock, but roughly 11 o'clock. So therefore you have to stay maximum 1 hour and 15 maximum. 1 hour 15 maximum. So therefore I don't give any break in between because no need to give a break. But try to keep your focus. Okay. Try to keep your focus. Try to keep your focus. Once you finish writing, raise your hands. Okay, finish writing. Okay, done. Okay, then yes, then okay, then we can talk about important application. Now, in addition to that, right. Now there is another way I want to tell you. This normal reaction forces acting in this way. Suppose if an object is on an inclined plane. Okay, suppose if an object is on an inclined plane, how to mark the normal reaction force? Okay, for example, it is not case 9, not case 9. Okay, case 9. Now this is an inclined plane. Okay, angle of inclination is, let's say, theta. This angle is theta. Now there's an object. That object is on an inclined plane. This object is on the inclined plane. How are you going to mark the normal reaction force? How are you going to mark the normal reaction force? Now, weight means always. Weight force always vertical downwards. Always weight towards the gravity. Always weight towards the gravity. Weight is always downwards. Always remember, weight always towards downwards. No matter what happens, weight always towards downwards.
But I told you normal reaction is perpendicular to the contact surface. Always normal reaction forces perpendicular to the contact surface. Now this is the contact surface inclined. If you mark the normal reaction force, normal reaction force on this object, capital R, perpendicular, am I correct? Am I correct? Normal reaction force on the surface, on the inclined plane, capital R. So mark this diagram also, it is important. So mark the normal reaction force on object by inclined plane, This is normal reaction force on inclined plane by object. Finished writing? Okay. Now we'll check whether we can do some questions. So we'll check whether we can do some questions. Once we're done doing, then we can go to now still normal reaction force. Still there are lots of things to learn regarding normal reaction forces. Still we want to learn more. So we'll check. Wait a minute. I will go through the tute. That tute. Here it is. Mechanics. Forces. Okay. Yes. Okay. Now in the take your tute and start doing. We won't do all the questions. Start doing question number 15. Page number 4. Question number 15. Simple A, simple B. Start doing simple A, simple B. Question number 15. Simple A, simple B. Start doing question number 15. Page number 4. Simple A, simple B. Now I think you can do it. You can do it. Start doing simple A, simple B. Now this question, now I have given the values, but in that question they haven't given the values. Therefore you want to find the answers in terms of a simple M1, simple M2, F. Okay, so you want to find the answers, acceleration and normal reaction forces in terms of simple M1, a simple M2, F. Got it? So doing that way, I will give some time. Start doing that question. Simple A and simple B. So then we are talking about normal reaction forces acting on lift. That story. Start doing. Now I also do with you. So I also do with you. Now question number 1, there are two masses. We want to find in that question we need to find acceleration of the system, tension. No. They ask acceleration and reaction forces. So I will do only first one. There are two masses M1, M2. It's easy. Question number 15 simply. I'm doing 15 simply. Then I will discuss next section. 15 simply. So you also keep on doing. Okay. There are two masses M1, M2. Applied force F. This one is M1. This one is M2.
if I mark the forces M1G weight downwards, M1G downwards, normal reaction force R1. I want to find R1 also, R2, normal reaction force R1. I want to find R1. Acceleration of the system, I want to find A. Normal reaction force R3, 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 and this one's weight is M2G. M2G, normal reaction force R2. I want to find R1, R2, R3 simply. Now we know vertical equilibrium, we can see now. If I consider vertical equilibrium, I know R1 equals M1G. It's not big issue. R1 equals M1G. And we know R2 equals M2G. Easy. R2 equals M2G. So remaining simple C homework. Then acceleration, entire system F equals M. System F equals ma. In the direction of motion, F equals ma. F equals ma. Then R3 cancel out. Only force is F. Only force F. System's mass M1 plus M2. You want to find answers in terms of F, M1, M2. Therefore, it's okay to keep M1, M2, F in your final answer. Then acceleration will be F over M1 plus M2. I got that answer also. It's easy. Now I want to find R3. Once I found R3, problem solved. R3. Now I thought of taking M2 and applying F equals M. M2 applying F equals M. I take M2. I apply F equals M. M2. I apply F equals M. F equals M. And then R3. R3 equals. Mass is how much? Simple M. Simple M is M2. Acceleration. This equation 1. From equation 1, I can write down acceleration as what? F over M1 plus M2. Therefore, my final answer will be M2F over M1 plus M2. Hands up, who got these values answer? Hands up, who got these values for A and R3? Who got these values answer? Before I get the answer, who got these values? There is one. I think you understand this idea. Okay. Simple B and simple C homework. So do simple B, simple C homework. If it is possible, do today itself. It's a homework. And now put your main topic. Now you understood normal reaction forces. Now normal reaction, simply, if I summarize it, normal reaction force means simply when there's a contact between two surfaces, the perpendicular force exerted on them is what we call as normal reaction forces. Then we have discussed about 9 cases. I think you have a good understanding about normal reaction forces. You have a good understanding. Please go through them again, refer them, prepare a short note by yourself. Okay. Now we are talking about, now you know that now all of us have used lifts. Lift means we can say elevators. We all have used elevators. Now, just think that you are inside an elevator. Now you are inside an elevator. Now when you get into an elevator, when elevator starts moving upwards until the floor that you want to get in, you feel different weights actually. You understand what I'm saying? So when elevator, be careful listen, when elevator starts moving, now you just get into the elevator, and when elevator starts moving, that means initially elevator is at rest. If elevator is to be moved, elevator must be accelerate initially. Am I correct? Because if elevator now, if an object is at rest, if an object suddenly starts moving, means object must undergo acceleration. Very similar manner, when you get into an elevator, when elevator starts moving, that means elevator must undergo acceleration. Now, when elevator starts moving, when elevator is undergoing acceleration, understand, you feel some kind of heavy in your body. So you are feeling some kind of heavy feeling, right? You feel that you have so much weight actually, right? Comparing with when your elevator is at rest, if you are standing on the floor normally, comparing with that. So when you get into the elevator and when elevator starts accelerating upwards, you feel that your body is so much heavy. You feel. How many of you feel in that way? Raise your hands. It's not that much of heavy weight because of that. It's not that much heavy, but you feel some kind of heaviness in your body. Hands up. How many of you feel that feeling? Hands up. How many of you feel that feeling? Hands. You guys have felt that feeling. Have that feeling. And next, okay, now elevator started accelerating. Then elevator is moving. When elevator reaches the required flow that you want to go, when elevator reaches the required flow that you want to go, that means when elevator comes to rest, elevator must undergo deceleration. Elevator starts moving. Once elevator reaches the required flow, elevator is decelerating. Elevator decelerating. When elevator starts decelerating, when it reaches closer to the flow that you need to go, your body feels some kind of lightweight feeling. You feel that you are not floating. It's not floating. You feel that some kind of lightweight feeling. So when elevator starts accelerating, initially you feel your body is heavy, and when elevator reaches the desired flow, you feel that your body is a bit light. Your weight is got decreased. So you might have felt that experience. That is because the reason for feeling heavy weight and lightweight, the reason behind that is change in normal reaction force. The normal reaction force felt by you is different. That's the reason. So when elevator is accelerating, normal reaction force felt by you is very high. That's why you feel that you are heavy. When lift is decelerating and reaching the desired flow, normal reaction force acting on you is low. That's why you are feeling low weight feeling. So we are going to explain that idea. And okay, put your topic, main topic, main topic, main topic. Write down man's motion on a lift. In a lift, man's motion in a lift. Man's motion in a lift. Okay. Write down under that, a man of mass simple limb. A man of mass simple limb. A man of mass simple limb. Standing in the lift. A man of mass simple limb standing in the lift. Now, case one. Case one. Case one. When the lift is at rest. Now, we are talking about few cases. 1, 2, 3, 4, 5. Now, case one. When the lift is at rest. When the lift is at rest. When the lift is at rest. Okay. This is a very important idea. Now, MCQs, you can find many MCQs from this section also. They can ask different questions from the section. We keep your focus until class finishes. Learn everything. Grab everything what I teach you. Grab everything. You people decided to do classes through online. Therefore, you should have a very good patience. Good patience. Okay. If I draw the lift, now case one, lift is at rest. Lift is at rest. Lift is at rest. Now there's a person inside the lift. This is my lift. Okay. If I draw the person, this is my person. It can be a girl, it can be a boy, it's up to you. So let's draw a boy. This is the boy standing on the lift. boy's hands. This boy's head. Shall we mark the forces now when that boy get into the lift and he's standing in the lift? If I mark the forces, how many forces acting on the boy? Can someone tell me how many forces acting on the boy? A boy standing on the lift. Can someone tell me how many forces acting on the boy? How many forces? How many? Anyone? Can someone say how many forces acting on the boy quickly? Can someone reply? Can someone reply how many forces acting on the boy? How many forces acting on the boy? Anyone? Can someone reply? Just reply. How many forces acting on the boy? How many forces acting on the boy? How many forces? Reply. There are only two forces. There are two forces acting on the boy. Weight of the boy downwards. I'm asking how many forces acting on the boy. There are two forces. Weight of the boy, I say simple mg downwards. Normal reaction force on the boy, because there's a contact between the feet of the boy with the bottom of the lift. There's a contact between the feet of the boy and bottom of the lift. So therefore, whenever there is a contact, there must be normal reaction forces. The normal reaction force on the boy, I say capital R. Normal reaction force on the boy, let's say capital R. Capital R, normal reaction, capital R. Now, when the lift is at rest, definitely man inside the lift also at rest. Am I correct? When the lift is at rest, definitely man inside the lift also at rest. That means the R must be equal to mg. If man is at rest, if the man is at rest, resultant force must be 0. Resultant force is 0 means resultant force acting on the man is 0 means R must be equal to mg. R must be equal to mg. I think that is not difficult. Write down once you know. Okay, case 1, draw this diagram. Draw this diagram, mark these two forces. And write down. When the lift is at rest, write down. When the lift is at rest. When the lift is at rest. Write down. Come on. The man inside the lift. The man inside the lift is also at rest. The man inside the lift is also at rest. Therefore, resultant force acting on the man must be 0. Therefore, resultant force acting on the man must be 0. Therefore, resultant force acting on the man must be 0. Now, write down capital R equals mg. Write down capital R equals mg. Capital R equals mg. Capital R equals mg. You can box it if you need. Case number 2. Finish writing, hands up. Finish writing, hands up. Finish writing, hands up. We finish writing, hands up. Okay. Case number 2, write down. Case number 2. Case number 2, write down. When lift moves under constant velocity, it can be upwards or downwards. When lift moves under constant velocity. Case number 2. When lift moves under constant velocity. Case 2. Lift moves under constant velocity. Constant velocity. Again, to the same diagram. Again, mark these two forces. Again, on the same diagram, mark these two forces quickly. Same diagram, mark the forces. There are only two forces acting on the person. Then weight simple mg downwards. Simple mg downwards. Normal reaction are upwards. Normal reaction are upwards. Write down. I'll ask a question. Now, Newton's first law says what? When there is no resultant force acting on the object, when there is no resultant force acting on the object should be at rest. If not, object should be moved under constant velocity. Now, this case number 2, lift moves under constant velocity. If lift moves under constant velocity, man inside the lift also moves under constant velocity. Am I correct? If lift moves under constant velocity, man inside the lift also moves under constant velocity. If man inside the lift moves under constant velocity means what? Resultant force acting on the man is 0. Again, resultant force acting on the man is 0 means again R upward must be equal to mg. Write down a point. Write down. If lift moves under constant velocity, write down. If lift moves under constant velocity, man inside the lift also moves under constant velocity. Man inside the lift also moves under constant velocity. Okay. Therefore, resultant force acting on the man. Therefore, resultant force acting on the man must be 0. Therefore, resultant force acting on the man must be 0. And then again write on R equals mg. R equals mg. R equals mg. Okay, case number 3, that is important. Now, the reason why you get heavyweight feeling. Case number 3. Hands are finished writing until here. Hands are finished writing until here. Quickly. Hands up, finished writing until here. Hands up, still writing. Quickly. Write on quickly. Case number 3. Case number 3, write down. Case number 3. Case number 3. When lift moves under, right? When lift moves under constant acceleration, simply. When lift moves under constant acceleration, simply in upward direction. When lift moves under constant acceleration, simply in upward direction. In upward direction. Case number 3. Now, this time, under acceleration, constant acceleration, okay? Constant acceleration upwards. Now, what will happen? Now, okay? Now, what will happen? Your lift person forces mg and r, forces mg and r, mg and r. This time lift is accelerating upwards. Simple A acceleration. Idea is very clear. When lift accelerates upwards, whatever the object inside the lift must also accelerate under same acceleration. That is important. Because when lift is accelerating upwards, whatever the objects inside the lift also should undergo same acceleration. So therefore, man inside the lift also accelerates under simply acceleration. Am I correct? Then man, there are two forces acting on the man. Upward is R, downward force on the man is mg. But you know that man in the lift must also accelerate upwards with simply acceleration. If man is to be accelerated upwards with simply acceleration, there must be a resultant force on the man upwards. If there is a resultant force on the man upwards only, we can ensure that man is accelerating. Because whenever there is an acceleration, there must be a resultant force. There are two forces. Then now what will happen? In order to accelerate the man under same acceleration, now R is increasing. Now R is increasing. R is increasing. That means your legs, your feet compressing now. Sometimes you don't do that intentionally, but automatically it's happening. When lift is accelerating upwards, basically what's happening, your feet compressing more the bottom of the lift. If lift is accelerating with larger accelerations, your feet compressing the bottom of the lift more and more and more. When your feet is compressing more on the bottom of the lift, you are getting larger reaction force. Okay, it is very clear, right? When your feet is compressing more, you are getting larger reaction force than weight. R is higher, mg is lower, resultant is R minus mg. Resultant is R minus mg. Because of that R minus mg, this one is accelerating. So therefore, I can apply F equals ma for the person. For the man, I can apply F equals ma upwards. For the man, I can apply F equals ma in the direction of motion upwards. F equals ma, resultant force, R upwards, mg downwards, R minus mg. R minus mg must equal to ma acceleration. If I subject R will be equal to, if I subject R will be equal to mg plus ma. Mg plus ma, if I take simple m as my common factor, simple mg plus a. See, normal weight of a person is mg. Normally, when you are standing on a floor, your normal reaction force equals your weight mg. Your R is equal to mg. But what's happening when you get into a lift? When lift starts moving, even when lift starts accelerating, now normal reaction, that R, normal reaction force acting on you is larger than the weight. That's why you are feeling that heavy weight feeling. That's why your body is feeling some kind of heavy feeling. Why? R is larger. Right? When R is 0, think that when R is 0, so when you are standing on a floor, there is normal reaction force on you. Normally, R is equal to mg. Think that normal reaction force acting on you is 0. You feel that you are light. You don't feel your weight. You feel like you are floating. You feel like you are flying. Right? The reason behind you feel your weight, reason behind you feel your heaviness is because of the normal reaction force acting on you. If the normal reaction force acting on you is larger, you are feeling your body so much weight. When you feel normal reaction force is lower, when the normal reaction force is lower, you feel your body is light. That's the idea. So box this one, R equals mg plus a, box. R equals mg plus a, box it. R equals mg plus a, box it. mg plus a, box it. Case number 4. Oh, no, we didn't write anything. I think we didn't write anything. Did you write something? Tell me someone, did we write something for case number 3? Did you write something for case number 3? Can someone tell me? We didn't write anything. Write down. Okay, write down. Okay, it's okay even once you finish writing also okay. If not, you can write down. When lift accelerates, comma, the man inside the lift also.
the man inside the lift also obtain same acceleration. Obtain same acceleration. Obtain same acceleration. Therefore, there must be resultant force. Therefore, there must be resultant force on the man. There must be resultant force on the man in upward direction. There must be resultant force on the man in upward direction. Therefore, normal reaction force acting on the man. Therefore, normal reaction force acting on the man. Therefore, normal reaction force acting on the man. Therefore, normal reaction force acting on the man becomes larger than the weight. Becomes larger than the weight. Becomes larger than the weight. Weight means mg. Okay. Write on this one. Right. Once you finished writing, raise your hands. Okay. If you finish writing, raise your hands. Once you finish writing, raise your hands. Once you finish writing, raise your hands. Now put your case number 4. Case number 4. Now follow what I say. Please try to follow what I say. That's important. Now, day by day, we are learning some complex concepts. Therefore, follow what I say. People who follow what I say, everything will happen smoothly. So follow what I say, because we do A levels. You guys are doing A levels, not to get fail, if not to get low marks, right? Because if you are doing A level math science streams, and if you will take CSW results, then what is the use of doing math science streams, right? It's impossible to get into medical faculties, obviously. If you in case if your result would be CSW, impossible to get into medicine. Definitely, it's impossible to get into medicine, and engineering also impossible, right? And some people, they say that I have a plan of doing engineering in a private institution, so therefore that's why I thought of doing A level in math subject. But the problem is, now these days, you know that now, in order to do engineering in a private universities, private campus, actually you don't need to do A levels in maths these days. So therefore, if you have an intention of doing engineering in private universities, even you are doing commerce, arts, then also you can do engineering in private institutions. So therefore, then when you plan to do, now you decided to do A level in math science streams, in that case, you should give 100% effort. 100% effort should be there. That is important. That is very, very, very important. Okay. If you always postpone doing something, if you always postpone doing something, the best example is if you always postponing watching recordings. If not, if you always postpone, okay, we'll look this not tomorrow. If not, we'll do these questions tomorrow. And temporarily, in that day, you do something else, and if you postpone doing works, then understand you can't survive in this field. That's the thing. You can't survive. You can't do something big in this field, math science. You can't do something big. Believe me. Many 90s, many 90s, you know what's happening, what the reason behind many 90s students get 9Ws in math science streams. You know what the reason? The reason is they think that they know everything. When students get 90s, the people, most of them, I don't say everyone, but most of them have an idea, have an intention that they have a kind of mentality that they know everything. So students who got 90s, they think that they know everything because they succeeded very well in their O levels. They got 90s. That means all the subjects they did well, they got A. So therefore, there is a mindset among them that they know everything. So therefore, sometimes when we say, as teachers, when we say, they believe that whatever I say, they don't accept because they have a mentality that whatever the things that they say, that is correct. So they have such mentality. That's the reason behind their failures. Because they don't follow what I say. If I say redo the questions, they don't redo it. Because they say that no, you used this already I did one time, and so when you explain also, I listen usually. Therefore, why should I want to do the questions again? They don't follow what I say. If I ask them to do past papers, if I ask them to do this one, they don't do that. Because we can't force them also, because they are also bright students, and we can't force them also. And then what will happen? They get 3Ws, they get 3S, 1C, 2S, if not 2C, 1 is useless. But you know, there are some students who their all result is low, but they love doing math science streams. For example, 2As, 3As, 4As, 5As. But those students do math science streams because they love doing math science. But when they do math science streams, that they know that they are very fear. There's some kind of fear among them because they are very afraid what will happen next. What will happen next? Will I understand this? Will I understand this? So because of that fear, they follow what teachers say. If I ask you to do this one, they do it. If I ask you them to do that one, they do. So because of the fear among them, they follow what teachers say. So therefore, they succeed at the end. That's why you might have seen people who got 3As. Ask from your, if you know the people, if you have your sister brothers who got 3As, ask from them what is your all result. What is your scholarship? It's not, doesn't matter. What is your all result? They say that I got 4As, 5As, 6As. Yeah, I got 9As, then I also got 3As, but most of the people, as the IT. Okay, therefore follow what I say. That's important. All right, then case number 3 also done. Case number 4. Case number 4, write down. Case number 4. When lift is decelerating. When lift is okay, case number 4, write down. When lift moves under, okay, right like this. Case number 4. When the lift moves under, when the lift moves under constant deceleration, constant deceleration, when lift moves under constant deceleration, in constant deceleration simply, when lift moves under constant deceleration simply in upward direction, in upward direction, in upward direction. Okay, the same story, draw the same diagram again, same story. Now decelerating upwards. Decelerating upwards means accelerating downwards. Decelerating upwards, accelerating downwards. Decelerating upwards, accelerating downwards. Case number 4. Decelerating, constant deceleration upwards. Constant deceleration upwards. Then in that case, lift the person inside the lift
Hands. Forces mg and r. Forces mg and r. Forces mg and r. Okay. Now you know upward direction deceleration means downward direction acceleration. Am I correct? Upward direction deceleration. Deceleration means downward direction acceleration. Okay, downward direction acceleration. So therefore, upward direction deceleration means negative acceleration. Am I correct? Upward direction deceleration means negative acceleration. Usually we apply F equals ma in the direction of motion. Usually we apply F equals ma in the direction of motion, right? If I consider the man and if I apply F equals ma, we usually apply F equals ma in the upward direction. Upward direction F equals ma. Now F means R minus mg. F means is upward direction R minus mg. F means R minus mg. R minus mg. Mass simple limb, but always remember F equals ma equation, simple A stands for acceleration. Simple A stands for acceleration. Simple A stands for acceleration, but upward direction, it is deceleration. Deceleration means we know negative acceleration. Deceleration means negative acceleration. Deceleration means negative acceleration. Okay. Somewhere else write down deceleration equals. Now I have given it as a note. Somewhere else write down deceleration means negative acceleration. Then you will end up with R equals this side subject R mg minus m simple A. That means mg minus A. Your R. That's why now see mg minus A, G minus A. Mg minus A means now your R is less than your weight. Mg. Now R is less than mg because now R is less than weight, less than mg. That's why when you reach the desired your flow, you get some kind of light feeling in your body. That's the reason why normal reaction force acting on you is lesser than the weight force. This R is lesser than the weight force. That's why you are feeling that you are light. Okay. Right on. I don't know, write down. Okay. Write down a point, write down like this a point. When lift decelerates in upward direction. When lift decelerates in upward direction, the normal reaction force acting on man. The normal reaction force acting on man. The normal reaction force acting on man is lesser than the, is lesser than the, is lesser than the, is lesser than the, is lesser than the weight. Is lesser than the weight. Okay. Right. Now, okay, now we discuss case number 1 and 2. Case number 1, when the lift is at rest. Case number 2, when the lift is moving under constant velocity. Both the cases, normal reaction force exactly equal to weight, mg. Case number 3, lift accelerates upwards. Case number 3, lift accelerates upwards. Then normal reaction force larger than the weight. Case number 4, when lift decelerates upwards, normal reaction force smaller than the weight. Now, case number 5 and 6. Case number 5, write down. Now, this time,
when lift moves under, case number 5, when lift moves under constant acceleration simply, when lift moves under constant acceleration simply, when lift moves under constant acceleration simply in down direction, in down direction, in down direction, in downward direction. Okay, now draw the diagram. Case number 5. Now you know what to do. This time lift is moving downwards. Case number 5. Lift is accelerating downwards. Constant acceleration downwards. In that case, what will happen? If I mark the forces, we mark the forces. Mg down, R up. Mg down, R up. Acceleration downwards. Acceleration downwards. In that case, apply F equals me downwards. Apply F equals me downwards the man. We draw, put man downwards F equals me. This time downward force mg, upward r, mg minus r. This time mg minus r, mg minus capital R must be equal to me. Acceleration downwards me. Then r equals again mg minus a. R equals mg minus me. That means m g minus a, that is r. Now you will get some kind of relationship between case number 3 and case number 5. I think no, not case number 3, case number 4 and case number 5. When lift accelerating downwards, normal reaction force also mg minus a. When lift decelerating upwards, then also normal reaction force mg minus a. See, important relationships. Finally, we'll put a small summary and we'll brief them. But now write down. Now also R less than weight. Now also R less than weight. Now also R less than weight mg. So okay, I don't give any. No, if you want write on a point, you can write on the point, same point. Okay. You can write on the same point if you want, but I don't give any point for that. Case number 5. Case number 6. Case number 6, write down. When okay, finish. Hands up, finish writing. Hands up, I'm going to finish writing. Hands up, I'm going to finish writing. Finish writing. Quickly. Okay, case number 6. The last, not last case, case number 6. Case number 6. Write down. When lift moves under constant deceleration, when lift moves under constant deceleration in down direction. Constant deceleration in downward direction. Okay. In downward direction. Right. Now this case, in this case,
mg and r, mg and r. Decelerating downwards, ni? Downward deceleration. Downward deceleration. In that case, applying F equals ma downwards. That means mg minus r, ni? Mg minus r must be equal to me when you subject r. When you subject r will be equal to mg plus me. Mg plus me. That means mg plus a. Mg plus a, that is your r. That means r is again larger than mg. Larger than weight. Larger than weight. Right? Now the summary, understand, if lift is at rest or moves under constant velocity, then there is no change in the normal reaction force. Normal reaction force exactly equals to weight mg. If lift moves under acceleration upwards, oh, very careful understand, if lift moves under acceleration upwards, oh, if not decelerates downwards under same values. If lift moves under acceleration upwards, or decelerates downwards under same value, same acceleration, same deceleration values, normal reaction forces are larger than the weight mg plus. Okay. If lift moves upward deceleration, no downward acceleration. If lift moves upward deceleration, no downward acceleration. Upward deceleration, no downward acceleration with same values. Then normal reaction force is smaller than weight mg minus. Hands up, how many of you really understood up to now? Everything is very clear. Answer. Raise your hands. Up to now, everything is very clear. Then you understood. I took time and I explained. This is very important. Try to understand. If you don't understand, ask questions whenever I'm free. I reply to you. Okay, so we'll write a summary. We'll write a small summary. Just summarize it. Okay, then okay. Red color will write an important summary. Red color an important summary. When a man inside a lift, when a man inside a lift accelerates upwards, or accelerates upwards or decelerates downwards, comma, then the normal reaction force on the man, the normal reaction force on the man, the normal reaction force on the man is greater than the weight mg. Therefore, man feels very heavy. Therefore, man feels very heavy during the motion. Therefore, man feels very heavy during the motion. Okay. Therefore, man feels very heavy during the motion. Now, next point was a red color pen. When a man inside a lift, decelerates downwards. Oh, okay. When a man inside a lift
accelerates downwards. When a man inside a lift accelerates downwards or decelerates upwards. Accelerates downwards or decelerate upwards. Then, normal reaction force on the man. The normal reaction force on the man. The normal reaction force on the man is smaller than the weight of the man, simple mg, is smaller than the weight of the man, simple mg. Therefore, man feels very light. Therefore, man feels very light during the motion. Therefore, man feels very light during the motion. Right. We'll do some sample questions and we'll decide to stop the class or continue until 10:40, 10:50. We'll do 2 sample questions and we'll check. Okay, write down sample question, sample question, write down. A man of mass 75 kilograms. A man of mass 75 kilograms stands in a lift. A man of a mass 75 kilogram stands in a lift. Full stop. What is the normal reaction force acting on him? What is the normal reaction force acting on him? What is the normal reaction force acting on him? When lift starts moving. When lift starts moving. When lift starts moving downwards. When lift starts moving downwards with an acceleration 2 ms minus 2. With an acceleration 2 ms minus 2. With an acceleration 2 ms minus 2. Find the answers. Once you found the answer, raise your hands. It's not difficult, it's easy substitution. Find the answers. Once you found the answer, raise your hands. Once you found the answer, raise your hands. It's very basic substitution. How many found the answer? Found the answer? Found the answer. What is the answer for that? Answer for that question is how much? How many of you got the answer as 600 newtons hands up? 600 newtons hands up. 600 newtons. Hands up. How many of you got the answer as 600 newtons hands up? Then 75 kilogram accelerates downwards. 75 kilogram accelerates downwards. 75 kilogram accelerates downwards. This equation. You can, when you are doing, you want to apply F equals ma downwards, then you want to derive all the things, then you want to get the answer. But I take this equation, I substitute acceleration downwards 75 kilogram. M is 75.
I'm going to find R. M75 mass, gravitational acceleration 10, accelerating downwards. Acceleration is 2, right? Then 8, 75 into 8. How much? 8 into 5, 40, 0, 4. 8 into 7, 56 plus 4, 60. This answer. Got the answer, right? Hands up who got this answer. Right, next ones, next sample question. Next sample question. Same idea. A man of no, a man of mass 75 kilogram, okay, standing in a lift, same thing. But the only difference is decelerative. Okay? A man of mass 75 kilograms standing in a lift, full stop. What is the normal reaction force on him? What is the normal reaction force on him? What is the normal reaction force on him? When lift starts moving upwards. When lift starts moving upwards. When lift starts moving upwards, with deceleration 2 ms minus 2, 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 with deceleration 2 ms minus 2. Upwards deceleration, upwards deceleration. Find the answer with me. Upwards deceleration. Hands up who got the answer. Hands up who got the answer. That is all 600, right? I told you, right? Accelerates downwards with same value O, decelerates upwards the same value. Acceleration in the R values are same. Okay. Now you can calculate it and you can get the answer, but that's the way. Learn by heart those things because they can ask MCQs from small tiny sections like this. They can ask them true false statements. Okay. Like this a statement like this: normal reaction force when the lift is accelerating upwards and decelerating downwards are same. Likewise, they can ask true false statements also. Therefore, be very careful. So you should 100% sure about the theory that you learned. Okay. Now, still normal reaction force almost finished, but still I want to talk about the reading of a spring balance. Not spring balance. The reading of a Bain scale. Bain scale. So that is under the concept of normal reaction force. Basically now, so when you keep a mass on a Bain scale, now sometimes you think Bain scale measures the weight. That's wrong actually. We all have a misunderstanding that. So the Dunu Taradi, that you know what's Bain scale, right? When you keep a mass on the Bain scale, sometimes we think that Bain scale measures the weight of that mass. That's wrong. Basically, Bain scale measures the normal reaction force on the Bain scale. So I will explain that idea next day. Now time is 10:45. Now raise your hands. Now today I think we learned lots of things. We discussed some questions also, but we could not do two questions yet because still I'm building the theories. But now I think you have a good understanding about forces, how this section is going. And now you might have felt that now it's somewhat complex also. It's complex, but it's not difficult. It's complex. Yeah, I agree with that. It's complex, but it's not difficult. Now, why smoothly I'm teaching you all the concepts from top to bottom without making any mistake. I'm teaching everything from top to bottom very clearly. Nicely, I am guiding you to the right path. Only you want to do is follow that path. I'm showing the path. Please go from here to here. I'm showing the path. I make you move the path. You only want to move it. You only want to go along the path. Okay? That's the thing. The thing is, people, they don't like to move. That's a problem. So I'm ready to make you move to the right place if you are interested to move. If you really want to move, I'm ready to make you to move to the right space. I hope you understand. Okay, right. So therefore, every day, whatever the questions that we did, because you don't have time to do now. Now I think we discussed some small questions today. Now we might have done every week. We do some questions. We do questions in the every week class. Now, do you have enough time to do them again and again? You don't have time, right? The questions that we did today. So will you do by yourself tomorrow, next week, again and again? You don't do it. You don't do it. Sometimes some students they do some different questions from past papers, model papers, tudes or other tudes or whatever. But you don't do the questions again. Me. That's why every day I say at least one last time, even you got the answers or even you didn't get the answers completely all right, one last time, one last time. Today itself, one last time, do the questions again. Because then you will know, you will never going to do the questions again. One last time, do it today itself, then finish. Chapter finished. That story is closed. Okay. Now I think you understood everything. Today we discussed lots of things. I couldn't start at 7:30 because my mobile phone didn't charge. The only charge was very low that time. That's why I took half an hour more. It did until 7:45, roughly 3 hours and 15 minutes. Okay. And study well. Study well. Okay. Then have fun. Okay, have fun. Study well. Have fun.